Hey class, welcome back to Chapter 9. So in Chapter 9 we're going to be talking about a few different topics. We're going to talk about center of mass, impulse, momentum, conservation of momentum, and different types of collisions like elastic versus inelastic collisions and so on. So there's quite a few different topics that we're going to be covering here. So I'll probably be breaking this into two different videos, but I want to start with an introduction to the center of mass, to impulse, and to momentum. So let's start with center of mass. So what the center of mass is as the name implies, it's the center of the mass of the object. So it's the point at which there's an even amount of mass distributed on all sides of that location. Okay, so for symmetrical objects that are homogeneous, meaning there's even density at all locations, then the center of mass is very easy to find. It's just the same as the geometric center of your object. But the center of mass for other things where you don't have uniform mass distribution are different. So for example, a fun example that one of our math professors uses is the idea of a can of soda. So as I drink this, it's not even soda, it's just flavored water basically, but it's carbonated, it's nice. But anyway, as I drink this down, with each sip, the center of mass actually decreases a little bit because there's more mass lower down when there's empty space up above. So the center of mass for my can is in the center across the top, but actually drops as I drink it lower and lower and lower until you get to the very bottom. As you drink the last few sips, it actually moves back up as it approaches empty, and when it's entirely empty, it's very close to the geometric center of your object. So center mass can really vary depending on the object and the way the mass is distributed within or around that object. But we care about paying attention to the center of mass because where it's at affects the way an object's going to move, and as you'll see in future chapters, it has to do with how it's going to rotate and other things as well. So you'll hear the term center of mass and center of gravity at different times. Near Earth's surface, these two terms are pretty much interchangeable, but there is a slight difference. Okay, so the center of mass and center of gravity, as I mentioned, are interchangeable because they're at the same exact location if you're on or near Earth's surface for relatively small objects. Okay, so they're interchangeable on Earth for everyday size objects, but there is a difference. So the center of gravity is the point at which there's an even distribution of weight force on all sides of the object, force due to gravity. Okay, whereas as we mentioned a minute ago, the center of mass is the point at which all mass is distributed evenly around that point. Okay, so the reason that we care about these ideas of center of mass and center of gravity is they really, again, as I mentioned before, help you describe its motion, and they also help you understand how to balance a given object. An object will always be balanced or supported if its base of support, the point at which it's being supported, is under the center of mass. So like here I have a plate, and so if I put my finger under the center of mass just right, I can actually balance it on that single point. If I'm off at all, as you can see, apparently I am a lot, then it won't balance quite right. But if I get perfectly under that center of mass location, then it will kind of balance. All right, well, not an amazing demonstration, but I had a plate sitting here, so that was from breakfast. Okay, so how do we define the center of mass? Well, you can actually quantify it quite simply. The center of mass is just going to be when you add up all the different masses and their locations, mass 1 times location 1 plus mass 2 times location 2 and so on, and divide by the total mass, that will give you the physical x location of your center of mass. So for example, here we have two different masses. Well, where's the center of mass? We know it's going to be somewhere between those two. All right, where exactly? Well, you determine the point of the first mass relative to some axis, the second mass, and then do m1 times the first position plus m2 times the second position. This dot 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 just represents if there's more masses, and then divide by the total mass of your system. You could put this axis anywhere, right? You could even have it passing through mass 1, in which case x1 would be 0, and you'd still find the same solution. Okay? So I wanted to kind of give you some examples of this idea of base of support needing to be under the center of mass, part of why we care about what the center of mass is. There's people, when it comes to loading airplanes, whose job it is, and this applies primarily to like cargo planes and stuff like that, but their job, they're known as the load master, and their job is to know where the center of mass is at all times, because when you have an airplane that's supported by just 3 little wheels, you have a set base of support that's relatively small. If that center of mass shifts beyond the base of support, if that center of mass ends up too far back, then the plane is going to tip over because it's no longer going to be supported, because you do not have your center of mass or center of gravity over the top of your base of support. And you see this a few different times. Here's 3 examples of cargo planes whose loadmasters probably are out of a job, okay? But just kind of cool other examples. I know something that I saw a lot when I was traveling on my recent juniors abroad trips, people stacking rocks, okay? In order to stack them, the center of mass of the rock on top must be directly over the point of contact between it and the rock below, because again, that's where its base of support is located. Here's a large rock. Where is its center of mass? I don't know exactly, but I know it's going to be somewhere above this portion of the rock, because that's where the base of the support is. Same thing here. And then here's a video of a crane who's lifting up this steamroller out of the middle of a bunch of traffic, all right? And watch what happens. As they move this roller, the center of mass of the system is gradually changing. You can observe as they get it going up, it's lifting, everything's good. The crane, quick question for you, okay? Now that that's off the ground, it's completely off the ground, where is the center of mass for the crane and the steamroller, that system? Where's its center mass? Where must it be at this present moment? Do you know? Well, it has to be under the physical footprint of the crane itself. So the crane is sitting there, has this arm extended out, and at the end of that arm is the steamroller. The center mass must be under the body of the crane in order for it to stay up. So I don't know if you've ever seen, we had a big crane come out to help us when we were building our house to pour the concrete. They have these big spider legs that go out and spread out really far in order to increase that base of support. So anyway, that's where it is at present, but let's see what happens as they start to swing this steamroller to try to get it out of the traffic. Ooh, the suspense. I'm guessing you probably have an idea of what might happen here. But as it starts to move, the base of support stays the same, but the center of mass gradually changed as I got a little further away, and look what happened to the crane. Again, because the center of mass was no longer over the base of support, and ended up crushing that car, unfortunately. So yeah, again, center of mass must stay over the footprint of the crane, otherwise bad news. All right, so that's center of mass. The next thing I want to just briefly introduce to you is the velocity center of mass. So that's talking about the speed at which the center of mass of a system is moving. So it helps you to quantify, again, the overall motion of an object by paying attention to the velocity of its center of mass. And its equation looks almost the exact same as that of the center of mass equation, but only with velocities. So again, you can have multiple different objects that are moving. So here you see 2 objects. The red and the blue object move and collide and bounce off of one another. But if you notice, the velocity of the center of mass does not change in this situation, even though the 2 objects will collide off of one another. And that's something we're going to talk about in more detail as we get into understanding linear momentum. But this idea of the velocity of the center of mass will give us a direct introduction to the concept of momentum that we'll see very soon. So just a quick example problem for you about the velocity of the center of mass. Here's 2 figure skaters, all right? They're starting off, as you can see, stationary. I give you their relative masses, all right? And you're watching this and you just decide, oh, I wonder what happens to their velocity of the center of mass of them. If I think of the 2 of them as a system, what's going to happen if they push off of one another? So you get out your phone, you make a video, maybe use that tracker video analysis software I told you guys about, and you find that the first skater, the male skater here, moves backwards at a speed of about 1.5 meters per second, while the other skater, the female skater, moves back at about 2.5 meters per second. All right? What's the velocity of the center of mass before and after the collision? So pause it, try it out, see what you get. The before, I'm guessing you can figure out pretty easily, right? Before, they're not moving, V1, V2, both 0, so the velocity of the center mass is 0. What about afterwards? Well, we have their masses, we have their velocities. You plug and chug, making sure you realize since he's moving backwards it's a negative 1.5 meters per second, and we find that the velocity of the center of mass stays at approximately 0 as they push off of one another. Since they're on an isolated system, isolated, anyway, since there's no net outside forces, it's only internal, you see that the velocity of the center of mass doesn't change. Interesting idea, interesting concept. It's going to come to play as we talk about more with momentum. All right, so this idea of center of mass, both the physical location and the velocity center of mass, can be also determined using calculus, right? Because if we're just summing up all of these different R values for each given mass, adding them up and dividing by the total mass of the system, when you have a lot of different chunks of mass, you can use integration to figure this out. All right, so if you integrate the location of each little dm, each little chunk of mass, you integrate all of those x dm's and divide it by the total mass of your system, and that will also give you your x center mass, y center mass, and z center mass. So this is something that a lot of times is done in Calc 2 or 3, I think. You'll be doing these volumetric integral center mass calculations and so on. I think it's usually in Calc 3 that we do it at Fox. But anyway, good application there for you guys to check it out. All right. So again, this capital M is the total mass of your whole object, all the little pieces added together. All right. So now I want to introduce the idea of momentum. What is momentum? Well, I'm guessing you probably heard the term, you've thought about or seen different applications of the idea of momentum. And you can probably figure out it depends on two quantities. It depends on the mass and velocity. Right? I used to play football back in high school and so on, and the amount of momentum somebody had was determined by how fast they're going, their velocity, and their mass. As somebody who was small, I needed to try to increase my velocity in order to have the same momentum as some of those bigger guys I would go against. So momentum is mass times velocity. Notice the little vector arrow on top. That means that momentum is a vector quantity. So the direction of momentum is the same as the direction of velocity, and it has units of kilograms times meters per second. All right. Now notice we use the letter P here, lowercase p, to represent momentum. All right. M was already taken by mass, and P actually, I believe it has roots tied to the Latin word that used to be used in place of momentum. Started with a P, and so that's why they use it. All right, so that's the idea of momentum. So now I want to think about momentum and Newton's second law, because that will help introduce to us the idea of impulse. So remember, Newton's second law says net force equals ma, right? Well, if you think about ma, a as a vector is really just the derivative of velocity with respect to time. Remember that, right? So net force can be thought of as m dv dt. Well, if you have a situation where your mass is constant, it's not changing with time, then you can pop the m into your derivative equation here, since it's just a constant that you're multiplying by, and you can say that the net force is the same as dmv, Department of Motor Vehicles right there, no, dmv over time, right? The derivative of momentum with respect to time. So really, you can restate, since momentum is equal to mass times velocity, net force is just the derivative of momentum with respect to time. And so let's start from this idea that net force equals the derivative of momentum with respect to time, and let's do a little bit of calculus on it. All right, so doing some algebra, right? We switch these around real quick, multiply both sides by dt, and so we have dp equals net force dt. If we integrate both sides, all right, what we get is that the change in momentum, integral of dp is just the change in momentum, is equal to the integral of force dt. And this idea, this concept right here, this quantity, the integral, the area under the force time curve, is just what we define as being called the impulse. So change in momentum is equal to your impulse, which is also equal to the integral of force times dt. Okay? So if we were to have the average force, just to help you visually see what we're talking about here, impulse, again, now we're using the letter J for impulse. You'll see later I was already taken. So we're using the letter J for impulse is equal to not only the change in momentum, but also the average force multiplied by the change in time. So again, integral of force dt, or average force times the change in time. And again, we're looking at a vector quantity, so they can have x and y components, don't forget. And our units here are newtons multiplied by seconds. So a lot of people are confused. Wait, I thought you said it's change in momentum. Shouldn't it be kilograms times meters per second? And now you're saying it's newtons per second? Do the math. They're actually the same. A newton is a kilogram multiplied by meter per second squared. Multiply by seconds, you get a kilogram times meters per second. So with both impulse and momentum, you can express it in terms of units of kilograms times meters per second, or newtons times seconds. All right? So let's talk about impulse in a little greater detail. Again, impulse is the change in momentum, right? Or it's the integral of force dt. So what we're saying is it's the area under the force times, or force versus time graph. Again, keeping in mind it's the net force. So the thing that gets tricky here is you can have two different situations with identical impulses. So right here, I've come up with this graphs. Both the yellow graph and the purple both represent equal amounts of impulse. Now, are they the exact same? No, they have equal impulses, equal areas, equal integral values, but they're not identical. What's different about them? Well, the difference is the force, right? Each one has a different force peak, so one is a smaller force over a larger time, whereas the other is a larger force over a smaller period of time. Whether you have the small force long time or large force small time, they both will give you the same overall impulse. So keep that in mind. A lot of people get confused. You can have the same change of momentum, but accomplish two different ways where you have different forces and times experienced. All right? So this gives rise to the impulse, or really is known as the impulse momentum theorem, just so you understand. Again, that tells us that the impulse is equal to the change in momentum. All right? Impulse equals change in momentum. So impulse, force times time, is change in momentum. So it really enables you to calculate a lot of different things. Quick kind of conceptual question I want you to think about. I don't know if you've ever noticed this, but if you've ever seen a car accident, right? I've seen a few different times where people have gotten accidents, or just seen a car after an accident. It's amazing the carnage that seems to occur. You have two cars that hit one another, and they both just get completely crumpled and smashed up in the front. So at first glance, when I was younger, I was like, man, cars just must be made really cheap. They're able to crumple so much. But in fact, engineers intentionally create the cars to be able to crumple at least a certain amount. I actually had a friend who one time got in an accident. Somebody turned out in front of her. She slammed into the side of him because he turned out so last minute, and her car crumpled all the way up, almost right to her knees, and then stopped and didn't crumple anymore. And she was able to walk away with minor injuries only. So my question to you all is, why? Why do engineers do that? What's the deal? Are they just cheap and they want body shops to make money? Or what? Think about momentum and impulse, pause the video, and then let's come back and see if you figured out why they do that. All right, so hopefully you paused it. Guess what? The reason that they do that, the reason they've designed the vehicles to crumple is because of impulse and force, right? Anytime you have a car wreck, right, ideally you try to minimize the amount of momentum exchange that occurs. But say you have two cars that are going to hit head on, each moving at 30 miles an hour. Okay? The amount of momentum that they bring in is fixed. You can't change that. So what can you change? Well, the only thing you can change is the impulse time, right? If you cause that car wreck to occur over a longer period of time, what happens to that maximum force experienced by the people in the cars? It decreases. The longer you can make the accident occur, or the longer it takes for the two cars to exchange their momentum and slow down as a result of their collision, the less peak force they will experience, and therefore the less damage that will occur to their bodies, right? The whiplash effect is a result of high force, high acceleration. So the more you can minimize that by increasing the impulse time, the better. There's other things too. I mean, if the cars were to hit and bounce back, you would have a larger change in momentum. So you don't want that to occur. But it's about increasing that impulse time, which decreases that maximum force. So here's another kind of idea. I don't know if you've ever used to do like an egg toss or a water balloon toss. You move back further and further and further, see how far you can toss it. Anytime, well, if you do it well, if you're not one of the first people out, the way you're probably catching the balloon or the egg is by moving your hands back kind of rapidly with the balloon as you catch it. What are you doing? So multiple choices time. Are you doing this in order to decrease the change in momentum, decrease the impulse, or decrease the force exerted by your hands? So again, pause it, think about it, what do you think? Boom, the correct answer, as you probably figured out by now, is answer C. You didn't change the momentum, right? It's going from whatever its velocity was to 0. So its change in momentum is fixed. Change in momentum equals impulse, so A and B are really just saying the same thing. The only thing you can do is increase the time that the collision is occurring and thereby decrease the force maximum exerted on the balloon to try to prevent it from breaking. Cool. So here's an example problem for you to try to use this for problem solving. So you take a ball, let's see, 0.4 kilograms. That's probably maybe something like a soccer ball. I'm guessing would have a mass in that range. So say you throw or kick a soccer ball at some wall. It goes towards the wall at 30 meters per second, hits and bounces. Let's assume it's straight back at 20 meters per second. Okay? Based on that information, I want you to tell me what is the impulse on the ball during that collision as it collides with the wall. So what is its impulse from the net force that it experiences? And if you were to like have a video and this collision is a well-inflated ball, happens very rapidly in just 10 milliseconds, if that's the case, what's the net force? Or sorry, not net force, the average force during that collision on the ball? Pause it, give it a go. All right, hopefully you paused it and gave it a go, tried it out. So we're trying to find the impulse initially, right? So just to remind ourselves, impulse is change in momentum or integral of force dt or average force times change in time. So to solve for the impulse initially, we don't know the force and we're given the time later, but we don't know the force. So to find the impulse, I'm going to start with, in part A, looking at the change in momentum. So again, impulse equals change in momentum. That means impulse in the x direction is changing the momentum in the x, and impulse in the y equals change in momentum in the y. This is a piece of information people a lot of times mess up. We're dealing with vectors now, so you have to think about x and y components. You can't just add 2 plus 2 and assume it equals 4 when you're dealing with vectors. Don't forget. So in this case, our impulse in the y is a piece of cake. It equals 0 since there's no y velocities, no y forces or anything else. So in the x direction then, what we're going to have is impulse in the x is equal to mv final minus mv initial, right? So now we plug in our values. M is 0.4. I factor that out since it doesn't change. My v final is a positive 20 meters per second minus my v initial, which is going in the negative direction, so it's a negative 30, minus a minus, right? Minus a negative gives us plus, so we have 0.4 times 50, so that should come out to be 20 newtons times seconds, or 20 kilograms times meters per second, right? And keeping in mind that we're dealing with a vector, that's just the x component, but the y component is 0, so the overall impulse is 20 newtons times seconds to the right in the positive x direction only. Boxworthy, boom. Okay, now part B, we want to find the average force. So we know impulse equals average force times change in time. So solving average force is going to be impulse over change in time. And again, you can break this into x and y components, don't forget, but we know our y component is 0, so there's no force in the 0, or sorry, no force in the 0. There's no force in the y direction, so it's equal to 0 newtons. And so all we're left with is finding the force in the x direction. So our impulse, which was 20 newtons times seconds over our 10 milliseconds, gives us an average force in the x direction of 2,000 newtons. Since that's the only force there is, it's boxworthy because the entire force is just 2,000 newtons to the right. So see the process. We started with looking at change in momentum and use that to find force based on the time. You could go the other way also. If you knew force and time, you could backtrack to try to find velocity or mass or other things. So be prepared to do that on upcoming homework. So here's a conceptual question for you all. Let's say you're driving down the road. We used to have a car that had hail damage, so it's an applicable example for my car is past. But imagine you're driving down the road and you have raindrops falling from the sky. All right, they're hitting your car all the time. Then a little bit later, those raindrops turn to hail. So let's assume that their velocity is the same as they hit, and the impact time, the amount of time it's in contact with your roof, is about the same, and the mass of each drop of water was the same as the mass of each hailstone. Which one will exert a larger force on your car, or are they going to exert the same? What do you think and why? So it's a little tricky. You're going to have to make some assumptions, but it's good. That's the way life happens, right? Physics of everyday life right here. So think about it, pause it maybe, talk to a friend if there's somebody there. If your mom's home, you know, say, hey mom, what do you think of this, you know? Anyway, so hopefully you figured out your guess. And the answer is, at least my answer is, that the hailstones will actually generate a larger force on your car. The reason for that is they would experience or cause a larger change in momentum. The raindrop's going to go from whatever that initial velocity is to 0, whereas the hailstone's going to go from whatever that initial velocity is to some negative velocity or positive, some velocity in the opposite direction as it bounces back up. So since you have a larger change in velocity and the mass is the same, you have a larger overall impulse, which means a larger change in momentum and a larger force acting on your roof since the time is the same. Okay, so again, I'm making the assumption that the hailstone's going to bounce off your roof and not just splat like a raindrop does, which, if it's a hard hailstone, would be true. So tricky conception. All right, so now I want to move on, all right? In chapter 7, I started with the work energy theorem and expanded that into talking about conservation of energy at the end of chapter 7 and into chapter 8. So now we've just introduced the idea of the impulse momentum theorem, telling us that the impulse equals a change in momentum, right? And now we're going to expand that into what's known as the conservation of momentum. But I want to prove to you how this works, okay? So in order to understand the principle of conservation of momentum, you need to first understand what I'm talking about when I say an internal force versus an external force. So any object or any system can really experience either forces from the outside, external forces, or internal forces which are within the object. So let's say the system is like my whole body, right? So if I clap my hands or hit one hand against the other, that's an internal force because it's all within my system. I'm pushing on myself as the hands hit off of one another. But if my dog were to come up and jump on me or something like that, that would be an external force. He's applying some outside force to me. Or earlier, we talked about those two ice skaters earlier in the video, right? We defined our system to encompass both of them. They're both part of our system. So as they pushed off of each other, that was an internal force to the system. But if they experienced friction or something like that, that would be an external force. So internal forces are within the system between different parts of your system. External forces are from something outside. Another example might be, say you're playing pool, billiards, all right? So you have all of your billiards balls and the cue ball. If you define that as your system, as they bounce off of one another, those would all be internal forces. But as any of them hit the sides or fall into the pocket, that would be an external force coming from something outside. All right? So we have the principle of impulse equals change in momentum, right? So I want to apply this now to a system. Let's say our system just involves any two objects. All right? So they can have internal forces between one another, and Newton's third law tells us for each force internally, you're going to have an equal and opposite force. So that's why you have F12 and F21. So let's say we look at the first object, the green object. Its net force is going to be any external force it experiences plus any internal forces, right? It's obvious. Net force is all the forces, outside and inside. Times time equals change in momentum. Same thing for the second object. You have any external forces times time, plus internal forces times time equals change in momentum for the second object. All right? So those are our two objects. Now, if we wanted to look at the overall system, we add those together. So everything experienced by the first object, its impulse and momentum, plus the impulse momentum for the second object to look at the system as a whole. If we add those together, we get one big, long, ugly equation. And because of Newton's third law of motion, these two internal forces are equal and opposite to one another. Therefore, boom, we can cancel them out. So what we find then is that the final momentum for the whole system minus the initial momentum of the entire system is just equal to only external forces times change in time. So since internal forces cancel out, what we're left with is only external forces can affect the momentum of a system. So when we saw those two figure skaters, even though there was an internal force as they pushed off of one another, the total velocity of the center of mass of the system stayed the same. The total momentum of the system stayed the same because it's only external forces that can change the momentum of a system. So again, it's only the sum of external forces times time that give us a change in momentum. So what does this mean? Well, what this means is if you can create a system that is free of external forces, that have zero net external force, what we define as an isolated system, isolated meaning it's free of any external forces. If you have an isolated system, then your momentum will be conserved. If you are in an isolated system free of any external forces, you will have conservation of momentum. But keep in mind, it's only in an isolated system. All right, people get confused by this sometimes. Okay, so for example, if you have a car driving down the road and it hits, runs into a wall or something like that, is momentum conserved? No, right? Even if you define your system as the object and the wall, it hits it, momentum's lost because the wall is attached to the ground. And so there's an external force from the ground on that wall causing it to lose momentum. But if you're doing bumper cars or like air hockey or something like that, your objects are just bouncing off of each other in an isolated way. In that case, you have conservation of momentum. So we're going to do a series of different problems using the idea of conservation of momentum. Something like bowling is a good example of conservation of momentum. The ball has a certain amount of momentum. It then hits one pin, transfers some of its momentum, sending that pin flying. It can hit another one, transferring momentum. And so the momentum that the ball started with is just being spread out amongst all these different parts of the system. But the overall momentum of the system stays the same until things start hitting the back of the bowling alley. So we're going to be trying to work with conservation of momentum. So always, you must first figure out whether or not you have an isolated system. So you need to define what objects are in your system. You need to then look at what forces are acting on your system, determine whether they're internal or external, and only if you realize or verify that all forces are internal and there's zero external forces, if that's the case, then you can assume you have an isolated system, and from there you can do sum of the momentum initial, add all those together and set it equal to the sum or the adding up of all final momentums, set those two equal to one another and solve, keeping in mind that you're dealing with a vector quantity, so you must do the x and the y together. So I'm going to do some sample problems of this. This video is getting a little long, so I'm just going to do one short example for you all here, and then I'll do some longer, more complicated examples in separate videos for you to see. So imagine somebody decides to do a test. So guns, I don't know if you've ever noticed, but they recoil quite a bit. I had a friend who one time was learning how to shoot and go hunting and different things, and he shot a rifle and the recoil kicked back. He wasn't ready for it, he wasn't supporting it properly, and the scope actually hit him and he came to work with a black eye the next day, sadly. Know your physics or else bad news. So here's someone who decides to just hold a rifle loosely. Maybe they're doing this in a lab in a safe way, and they're going to fire it, and the bullet's going to shoot out one side and the gun is going to recoil as a result. And so he wants to calculate to predict what the recoil is going to be and then see whether or not experiment verifies his prediction. So let's say that the overall rifle has a mass of like 3 kilograms and the bullet being fired is 0.05 kilograms, so 50 grams. It's kind of a small bullet. Realistically, it'd probably be a little more massive than that, but we'll go with that. And so let's say that this rifle can shoot the bullet at a speed of about 300 meters per second. What is the recoil velocity of the rifle? So we're going to try to solve this problem. We're going to assume it's hanging loosely, it's free of external forces, so we have an isolated system. All right, so here's our bullet. It's going to shoot forward with some momentum. The gun's going to move backwards with some recoil momentum as well, and we want to try to solve. So the first question is, thinking about our momentum, right? Conservation of momentum. What's our initial momentum and what's our final momentum? Pause the video, think about it, see if you can solve and get an answer. Okay, so hopefully you did. And guess what? In this situation, the final momentum is the momentum of the gun plus the momentum of the bullet. And the initial momentum is 0 because they're both stationary. When you first pull the trigger, they're both stationary. So this is interesting, right? Momentum here is going to be conserved. What about energy? Is energy going to be conserved? Well, not mechanical energy, right? Because the initial energy is 0, and then there's obviously both things have energy afterwards. Do we just magically make up energy? No, right? It was stored in the form of chemical potential energy in the gunpowder that was ignited. So that's where the energy came from. But we can use conservation of momentum. So this is one of the powers of conservation of momentum, when sometimes energy will not suffice. All right, so the momentum of the gun and the bullet, as we can see, must be equal and opposite to one another, since the system started with 0 initial momentum. So momentum is just mass times velocity for the bullet and for the gun. So here we can see the momentums are going to be equal and opposite to one another. We want to find the final velocity of this gun, right? So if we do algebra and solve for the velocity of the gun, we find that it's negative 5 meters per second. Now, where did this negative come from? Well, the negative came from the fact that it's shooting backwards in the opposite direction that the bullet was shot. So again, just make sure you pay close attention to the process. It's an isolated system. You establish that. You then set up final momentum equals initial momentum. Figure out what your final momentum components are, what your initial momentum is, and then solve. Now notice here, everything was in the x direction, so I didn't have to break things down into vectors. If you have things moving in multiple directions at once, you'll then have to use vectors. All right, so I think this video is pretty long at this point, so I'm going to stop here. I'll have some other examples for you guys in separate videos to look at more complex ones, and then tune in for the second half of Chapter 9, where we talk about inelastic collisions, elastic collisions, and looking at momentum in 2 dimensions. Have a box-worthy day.